Okay, so we were discussing about the insertion and deletion algorithms in AVL tree. AVL tree are balanced binary search trees, okay, which can be used as a search tree, but the height of both the left and right subtrees of each node is balanced. Okay, and to keep the AVL tree balanced, we perform rotations, and three kinds, in fact, four kind of rotations can be performed: LL, RR, LR, and RL. Okay, and this depends on in which subtree the new node is inserted. If the new node is inserted in the left subtree of node A, then it is called LL rotation. You need to perform LL rotation. And what is node A? Node A is that node for which the balance factor is not -1 or 0 or 1, and that node is the nearest ancestor to the inserted node on the path from the inserted node to the root node. Okay, so to perform the insertion, you first identify node A. Okay, and once you have identified the node A, then you perform the rotation. Okay, either LL, RR, LR, or RL. So we have discussed LL and RR notation. Okay, now RR rotation. Sorry, we have already discussed RR. Now LR rotation. So in the LR rotation, the inserted node is in the right subtree of the left subtree of the node A. Okay, for example, see this tree. Okay, so you can see the structure of this node. The height of AR means the right subtree of node A. The height is H, right? The left subtree of node B, that is BL. The height of BL is also H. Okay, the height of CL is H minus 1 less than the height of BL. Okay, so the height of CL is H minus 1. The height of CR, the right subtree of node C, is also H minus 1, so its balance factor is 0. Okay, so the height of CL is H minus 1. Okay, so height of this tree, that is, which includes the subtrees of node C plus the node C itself, the height will be H minus 1 plus 1, so it will be H. Okay, so height of both BL and BR are same, so the balance factor for node B is also 0. Okay, and the height of left subtree of node A will now become H plus 1, and height of AR is H, so difference is plus 1. The balance factor for node A is plus 1. Okay, now you insert X, a new node X, into CL here. Okay, so here X is inserted into CL. So what is the position? Okay, first you identify node A. What is node A? Node A is on the path from inserted node to the root node, and the balance factor is not equal to -1 or 0 or 1. So what is the path? This is the path from the inserted node to the root node. Okay, and these are the updated balance factor for all those nodes on this path. So we have +1 for node C, -1 for node B, and +2 for node A. Okay, so the nearest ancestor on this path for X is the root node. That is the node. The root will be the node A. Okay, because it is imbalance. The balance factor is +2, and it is the closest node to the node X on this path. Okay, so you have identified node A. Now see the position of X with respect to the node A. Node X is in the left subtree of node A. Okay, and it is in the right subtree of its left subtree. Okay, so node X is in the right subtree of the left subtree of the node A. So the rotation that you will perform will be LR, because node X is in the right subtree of the left subtree of node A. Okay, now how the rotation will be performed? Okay, so you have identified node A. Let's call the root of the node A's left subtree as node B, and let's call the root of the right subtree of the left subtree of node A as C. Okay, so identify two more nodes, node B, which is the root of the left subtree of node A, and then identify node C, which is the root of the right subtree of the left subtree of node A. Okay. Okay, so now you identify node A, node B, and node C. Now, how the LR rotation will be performed? Okay, LR rotation. Node C is made the root of the rotated tree. Okay, you have identified node C. Node C is made the root. Okay, and node B will make its left child, and node A will be made as the right child of node C. Fine. Okay, now node C had both CL and CR. It had both left and right subtree. The CL, that is the left subtree of node C, will be made the right subtree of node B, and the right subtree of node C will be made the left subtree of node A. Okay, so CL, the left subtree of node B, is made the right subtree of node B, and the right subtree of node BCR is made the left subtree of node A. Okay. So basically you have to adjust these four edges. Okay. B is made the left child of node C, node A is made the right child of node C. The left subtree, the entire left subtree of node C, that is CL, is made the right subtree of node B, and the right subtree of node C, CR, is made the left subtree of node A. Okay. So you have to adjust these 4 pointers. Now the example of LR rotation. So this is the AVL tree. Balance vector of all the nodes are okay, either 0, -1 or 1. Okay, now you insert 37. Where the 37 will be inserted? You start from the root node 44. It is less than 44, so you go to the left subtree of it. Okay, 30, it is greater than 30, so you will go to the right of this, and it is less than 39, so you will go to the left, and left subtree is empty, so 37 will be inserted there. Okay, now if after insertion of 37 you calculate the balance vector of each node, okay, and you found that the balance vector of A now becomes +2. Okay, so now you find the node A. Okay, so path from the inserted node to the root node is this, and the balance vector of uh, all the nodes are calculated. Okay, and you found that this node, the root node, that will be the node, is the node A, because it is imbalanced and it is the closest node, the closest imbalanced node to the inserted node 37. Okay, so you have identified node A, then identify node B and C. B is the root of the left subtree of node A, and C is the root of the right subtree of node B. Okay, so once you have identified node A, B, and C, you will perform the LR rotation. So in the LR rotation, the node C is made the root. So node C 39 is made the root. Okay, and the node B 30 is made the left child along with its left subtree. Okay, and node A will made the right child of node C. So A is 44. So A is made the right child of node C along with its right subtree. Node C has left subtree, but it has no right subtree. So left subtree of the node C is made the right subtree of node B. Okay, and the right subtree is made the left subtree of node A. So right subtree is empty, so left subtree of node A will also remain empty. Okay, so this is the final tree. So this is LR rotation, and similarly RL rotation can be performed. Okay, RL rotation is exactly mirror image of the LR rotation. You have to just interchange left with right and right with left, and you will get RL rotation. Okay, when you will have to perform the RL rotation, when the new node is inserted into the left subtree of the right subtree of node A. Okay, so first you will identify node A and then see if the new node is inserted into the left subtree of the right subtree of node A, then you will have to perform RL rotation. And in the RL rotation, the same step is performed. Okay, that is first you will identify node A, then node B and node C are identified, and the same structure, the same thing will be performed, except that the right will be interchanged with left and the left will be interchanged with right. Okay, that is in that case also node C will be made the root. Okay, and here you know okay, so in fact it is the exact mirror of the LR rotation. Now see some more example of insertion into AVL tree. Okay, insert 64 and 1. So 64 will be the root node, then you insert 1. So it will be inserted in the left subtree of it. Okay, then you insert 14. Okay, so 14 is less than 64 and it's greater than 1. So 14 will be inserted over there, but it will make node A, node 64 imbalance. Okay, so now you see that new node 14 is in the right subtree of the left subtree of the 64, right? So A is imbalanced and is the closest ancestor to 14, the new node. So it is the node A, right? And which rotation will be performed? Because 14 is in the right subtree or the left subtree of node A, so you have to perform LR rotation. Okay, so identify node B and C. Node B, okay, which is the root of the left subtree of node A, and node C, which is the root of the right subtree of node B. Okay, so what we'll do, you will rotate using the LR rotation. How the LR rotation is performed? Here it is. Okay, node C is made the root with B as left child and A as the right child, right? So here C is made the root. Okay, node B is made the left child along with the BL, okay, which is empty, and A is made the right child along with AR, which is also AR is also empty, and CL and C are also empty. Okay, so the right subtree of B will be empty, and also the left subtree of A will also be empty. So this tree will be achieved. Now insert some more elements. Okay, and inserting these elements does not make the tree imbalance. Okay, you insert 36, 13, 110 and 98, you will get this tree, and then insert 85. Okay, so 85 will be inserted, 64, 98 here, sorry, here as the left child of 98. Okay, but inserting 85 will make several nodes imbalanced. Okay, this is imbalanced, this node is also imbalanced, this node is also imbalanced, right? So find node A. Node A is the closest ancestor which is imbalanced and which is also on the path from the inserted node to the root node. So this is the path from the inserted node to the root node, and there are several imbalanced node on this path, which is the closest one to the new node. This is 110. So your this node 110 will be the node A. Okay. Now find the type of rotation. the new node X is in the left subtree of the left subtree of node A, so it means you have to perform LL rotation. Okay, and then you perform LL rotation and then you obtain this tree, right? So this is the method of inserting elements into the AVL tree. Now deletion algorithm. The deletion algorithms are almost same as the insertion algorithm, right? So let's see them. Uh, we identify the node A, okay, and node A is same as the node A for the insertion algorithm. That is, node A is that for which balance factor is neither -1, 0, or 1, and it is the nearest ancestor to the deleted node on the path from deleted node to the root. Okay, the definition of node A is same. Okay, once you have identified node A, then you identify if the deleted node is in the left or right subtree of node A. Okay, and then you find the balance factor of node B. And what is node B? Node B is the root of either left or right subtree of node A. Okay, and when it will be left or the right subtree, when it will be the root of the left or right subtree of node A. If the deleted node is in the left subtree of A, then node B is the root of node A's right subtree. Okay, and in the second case, if the deleted node is in the right subtree of node A, then node B is the root of node A's left subtree. Okay, so deleted the node is in one subtree of node A, and node B will be in the other subtree of the node A, will be the root of the other subtree of node A. Okay, so in fact, 6 different cases can be identified for deletion: 3 for right and 3 for L. Okay, it is okay. So 3 for right cases and 3 for left cases. Right cases are those cases in which the new node is inserted into the right subtree of the node A. Okay, and when the node is inserted in the left subtree of node A, it is called left rotations. And we have 3 kinds of R rotations and 3 kind of left rotation. Okay, so if the balance factor of node B is 0, it is called R0. Okay, that is, a node is deleted. Sorry, node is deleted from the right subtree of node A, and the balance factor of node B, which is the root of the left subtree of node A, is 0, then that rotation is called R0. Okay, R1, when the balance factor of node B is 1, and R minus 1, when the balance factor of node B is -1. Okay, note that the balance factor of node A is imbalanced, not equal to 0, 1, or -1. But the balance factor of node B, which is the root of either left or the right subtree of node A, will be balanced. So it will be the 0, 1, or -1. Okay. So for the right, that is when the node is deleted from the right subtree of node A. Okay, in that case, node B will be the root of its left subtree, the node A's left subtree. So that case will be either R0, R1, or R minus 1. R, because the node is deleted from the right subtree of node A, and 0 means the balance factor of node B is either 0, R1 when it is 1, R minus 1 when it is -1, and node B is the root of the left subtree of the node A. Likewise, you can define L0, L1, and L minus 1 notation. Okay, so L means node is deleted from the left subtree of the node A, and in that case, node B will be the root of the right subtree of the node A, and if its balance is equal to 0, rotation will be L0, and if it is 1, it will be called L1, and when the balance factor of node B is -1, the rotation will be called L minus 1. Okay, so L rotations are exact mirror images of R rotations. Okay, you have to just interchange left with right and right with left. So we will discuss only the R notations, R0, R1 and R minus 1, and then you can obtain R rotation by interchanging left with right and right with left. Okay, so what is R0? Deleted node is in the right subtree, that's why we have the first letter R, and the balance factor of node B is 0. So second is 0. So we have R0 rotation. Okay, so let's discuss them one by one. R0, R1 and R minus 1. So R0. So this is the tree. Okay, and you can see that the height of BL, left subtree of node B is H, height of BR is also H, the height of AR, the right subtree of A is H. Okay, so the height of the left subtree of node A is H plus 1, so its balance is plus 1. Now you delete X from AR. Okay, that is, you delete X from the right subtree of node A. So now the height of AR will become H minus 1. Okay, because you have deleted X from AR, so H minus 1. Now the balance of node A is plus 2 now. Okay, H plus 1, height of its left subtree, and the height of right subtree is H minus 1, so difference is plus 2, right? Okay, so now identify the type of rotation which is to be performed. First identify node A. Okay, node A is this. Okay, the closest ancestor of the deleted node which is imbalanced. So node A is this. Okay, and then what you will do, you will perform okay, then you see in which subtree the deleted node is. The deleted node X is in the right subtree of A. Okay, so it is in the right subtree, so you write R. Okay, and then identify node B. Node B is the root of the left subtree of node A, because the deleted node is in the right subtree, so node B will be the root of the node A's left subtree. So this will be the node B. Okay, and you see that its balance is 0, so the rotation R0 will be performed. And how R0 will perform? Okay, the R0 notation is exactly same as LL rotation, which is used for the insertion. Okay, so the number of steps in the R0 rotation is exactly same as the left rotation for insertion. Okay, so you can see that the node B here is made the root node along with its left subtree. Node A is made the right subtree, the right child of node B along with its right subtree, and the right subtree of node B is made the left subtree of node A. Okay, these three steps are performed, and these are exactly same as the LL rotation, right? Okay, now after insertion, you can see that the balance factor of node B and node A are minus 1 and plus 1. Okay, earlier, before performing R0 rotation, the balance factor of node A was plus 2, and for node B it was 0. After performing R0 rotation, it will be plus 1 for node A and minus 1 for node B, right? Now example, so you can see if you try to delete 60, okay, this node from this tree, okay, so deletion of 60 will made this 3 imbalance, because the balance factor of 46 will become plus 2. Okay, so the deleted node, okay, so you identify node A. So this is the path from the deleted node to the root node. Okay, and the closest ancestor which is imbalanced on this path is node 46. So 46 will be the node A, right? And deleted node is in the right subtree of node A. So one of the R rotation will be performed. Okay, which one? 0, -1 or 1. So for that you identify node B. Since deleted node is in the right subtree, so B will be the root of the node A's left subtree. Okay, so this is the left subtree of node A and its root is node 20. So root 20 will be your node B. Okay, and its balance factor is 0. So R0 rotation will be performed. And R0 rotation is exactly same as LL rotation. Okay, so node B will be set as the left, sorry, node B will be made the root along with its left subtree. Okay, node A along with its right subtree will made the right child new root node, node B. Okay, and the right subtree of node B will made the left subtree of node A. Okay, exactly same as the LL rotation. Okay, now R1 rotation. R1 rotation means R means that the deleted node is in the right subtree of node A and the balance factor of node B is 1. Node B is in this case is the root of the left subtree of node A. Okay. So for example here in this case node X is deleted from here from the right subtree of node A. Okay. And the balance factor of the root of the left subtree of node A is plus 1. So it is R1 notation. And R1 notation is also exactly same as LL notation. There is a number of steps which are performed, number and type of steps which are performed in R1 notation is also same as LL notation. It means that both R1 notation and R0 notation are same because both are same to the LL notation. Okay, so it means R1 notation is also same as R0 notation. The only difference is that you obtain different balance factors after performing rotation, right? So here you can see that the same steps are performed. That is, node B is made the root along with the left subtree, and node A is made the right child of node B along with the right subtree, and the right subtree of node BR is made the left subtree of node A. The same steps are performed. Okay. The difference is that you obtain different balance factor after performing R1 rotation. Okay. So you can see that the balance factor of node B is 0 and balance factor of node is also 0 after performing rotation. In the R0 rotation, the balance obtained balance factors were -1 for B and +1 for A. But in the R1 notation, you obtain both nodes, that is node A and node B's balance factor as equal to 0. Okay. So steps performed are exactly same, but different values for the balance factor of both node A and node 0 are obtained. Okay. So this is R1 notation. This is an example. Okay, here you delete 39. Okay, so the balance of node A is now +2. Okay, so 37 is your node A. Since deleted node is in the right subtree, so it is R rotation. The root of left subtree is node B and its balance is 1. So you need to perform R1, right? So how R1 will be performed? Node B will be made the root along with its left subtree. Okay, and A along with its right subtree will make the right child of node B, and the the right subtree of node B will be made the left subtree of node A. The right subtree of node B is made the left subtree of node A. Okay, and you can see that balance factor of node B and A are same. Both are equal to 0. So this is R1 notation. Now R minus 1 notation. Okay, the deleted node is in the right subtree, but the balance factor of node B is equal to -1, where node B is the root of the left subtree. Okay, so node is deleted from the right subtree of A, and the balance factor of B is -1. Okay, so R minus 1. How R minus 1 notation will be performed? You identify node B and node C also. B is the root of the left subtree of A, and C is the root of the right subtree of node B, right? So node C here is made the root, and B is made the left child of C, and A is made the right child of C. Okay, so it is not equal to LL rotation. In fact, it is similar to the LR rotation. Okay, so C is made the root, B is made the left child of C, A is made the right child of C. Okay, BL will remain the left child of B, and AR will remain the right subtree of A. The left subtree of node C, CL, is made the right subtree of node B, and the right subtree of CR is made the left subtree of node A. Okay, so these four adjustments will be performed. Okay, that is node B. Sorry, first you made node C as the root. Okay, and then the node B along with its left subtree is made the left subtree of node C. Okay, and node A along with its right subtree is set as the right child of node C. The left subtree of node C is made the right child of node B, and the right subtree of node C is made the left child of node A. Okay, so these four steps are performed. Example of R minus 1. So here you delete 52. So 52 is in the right subtree of 44. Okay, so you identify the path. Okay, you find the balance factor -1. Okay, so it is before deleting 52. You delete 52 and then you obtain the path and the balance factor of all those nodes on that path. So it is 0 for node 48 and +2 for 44. So the closest ancestor of deleted node 52, which is imbalance, is 44. So your 44 node is node A. Okay, since 52 is in the right subtree of node A, so right rotation R, and node B, which is the root of the left subtree of node A, the balance factor for node B is -1. So R minus 1 notation. Okay, now also identify node C. Node C is the right subtree of node B, the root of the right subtree of the node B. So node 28 is your node C. So how to perform R minus 1? Node C is made the root, so 28. Node 28 is made the root of the AVL tree. Okay. Now the node B along with its left subtree is made the left child of node C, right? Node A along with its right subtree is made the right child of node C. Okay. The right subtree of node C, the left subtree of the node C is made the right subtree of node B, and right subtree of node C is made the left subtree of node A. Okay, so that's R minus 1 notation, and that is exactly similar to LR rotation. Okay, so similarly, you can define L rotations. Three kind of L rotations can be defined: L0, L1, and L minus 1, right? So when the deleted node is in the left subtree and the balance factor of node B is either 0, 1, or -1, Okay, and what is node B in this case? Node B is the root of the right subtree of node A. Okay, now see an example of deletion. So you have this AVL tree, balanced binary tree. Now delete 120. Okay, 120 is here. You delete 120, and after deleting 120, the node is still balanced. The AVL tree is still balanced. Okay, because the balance factors are all the nodes are either 0, 1, or -1. Okay, deletion of 120 is very easy because it is the leaf node. So this is the case one of the deletion algorithm cases for the binary search tree. So it will be deleted very easily. Okay, now delete 64. 64 will be deleted from here. This is the case 3. Okay, so it will be replaced with its in order successor. So 85 is the in order successor, so it will be deleted first. So it is the leaf node, so case 1. So 85 is deleted, and then it will be put in place of node 64. So again, very simple. Okay, now delete 130. Okay, when you delete 130, now the resulting tree is imbalanced. Okay, so deleted node is 130. Its path from itself to the root node is this. Okay, find the balances 0 and +2. So node 120 is the closest imbalance node on the path from the deleted node to the root node. So node A will be this one, 128. The root node is the node A. Now the deleted node is in the right subtree of node A. So you need to perform R rotation, okay, to make the AVL tree balance, and find the node B. Node B is the root of the left subtree of node A. So node 98 is the node B, and its balance factor is 0. So you need to perform R0 rotation. Okay, how you will perform R0 rotation? Which is exactly same as LL rotation. Okay, so node B will be made the root, okay, along with its left subtree, and node A along with its right subtree will be made the right child of node B, and the right subtree of node B will be made the left subtree of node A, right? So this is R0 rotation.